A little lower. Come down. See, just flip the... That's fine.
Here's a shadow of a hand cast by a small light source. It's quite sharp. That's because the light coming from the source goes past the edge of the hand in straight lines. There's bright light in here. The shadow itself is quite dark. This is good evidence for the fact that light travels in straight lines. If I use a bigger light, I get a fuzzy shadow. Light is still going from one part of the source past the edge of the hand and creating a sharp shadow because it goes in straight lines. But from a different part of the source, light comes past the same edge at a slightly different angle, and it illuminates the area of the shadow cast by the first beam of light. In this way, we get a fuzzy image. We come in contact with shadows in our everyday life. Some are fuzzy, some are sharp. They're common sights. We can see the same sort of thing on a cosmic scale if we look at a shadow of the Earth cast on the moon. The shadow has a fuzzy edge simply because the sun subtends an angle of nearly 1/2 degree at the Earth. The shadow on the moon is really a whole set of overlapping shadows cast by the various bright parts of the sun's surface. The sun is too big to cast a sharp shadow. Now, how sharp can a shadow really be? In order to experiment with this, we need some progressively smaller light sources. I have 3 zirconium crater arcs here that are very good for this kind of work. This big fellow is awfully bright. It has a neutral density filter on the end of it here because I'm concerned really not with the intensities of these 3 lights, but with the sizes of the craters themselves. This one is a smaller crater, and this one is still the smallest of the bunch. In order to measure the size, the diameter of these craters, I'm going to put a lens in here and a piece of card on the end of the optical bench. Then if I turned on these lights and measured the distance from the craters to the lens, and then from the lens to the card, and then measured the size of each of the images on the card, I could compute mathematically just how big these are. I'm not going to do it because you wouldn't see it very well, but I have done it, and this one I know is 2 millimeters in diameter. This is 0.65, and this is 0.15. Now, I want to show you just how big these are by projecting the sources onto the film in the camera through the camera lens. In order to do this, I'll turn on the first. There it is. Now the second. There she goes. And the third one. There. You can see the relative sizes quite clearly, I'm sure. Now to cast some shadows, let's use this screen wire mesh in here. To cast shadows, I don't want the lens in the camera. I'm not making an image of the screen, but casting shadows directly on the film. Turning out 2 of these sources. I have just the big one going. You get a nice sharp image in there. And if I bring the screen toward the source so that the shadow gets bigger, you see that when I reach about here, then it begins to get quite fuzzy. This is what you'd expect because the diameter of the crater is actually larger than the size of the wire in the screen. Now if I use the medium-sized light, there it goes, I can cast shadows again. This time they're sharp. They stay sharp for a somewhat longer period. But when I get back about here, there, now they're starting to get quite fuzzy. And again, you'd expect this because even this source is fairly large compared to the size of the wire. Now the third experiment will involve using the smallest source of all. There it goes. There's the shadow on the film, just as we had before. It's quite sharp. As I move the screen away, it stays sharp for quite a bit longer time than the others did. But then when I get it about in here, then you start to see something funny happening. In the shadow of the wire itself, you see bright and dark lines, and in the space between, you see sort of a Scotch-Plaid effect. And it might be due to the fact that we have a regular arrangement of wires here in this screen. Let's try a different material and see if we get the same sort of effect. I have a needle mounted on a stand. I can put this in front of the light source and cast a shadow on the film. You know what a needle looks like. There it is. It's a good, sharp shadow. As I bring it back toward the source so that the shadow is bigger, I get the same sort of effect. I begin to get bright and dark regions in the shadow of the steel around the eye of the needle. And in the eye itself, I get a sort of mixed-up set of bright and dark lines. So, it's not the material or the arrangement of the material that does this. It must be a property of light itself. Now, you can see this sort of thing on your own by doing a simple experiment. I have one way of doing it right here. These are tongue depressors mounted so that they can be closed down and making a narrow slit right in between two of them. Any convenient light source will work. I have a simple one here that you might find available. It's called a showcase bulb, and I use it because it has a narrow filament. Now, if I hold this up and align it with the light source, then close down gradually, and if you did this, this is what you'd see. To be sure, the camera is a little different from your eye, and I have to adjust the slit to make it come out well. But notice that as the slit is narrowed, the light spreads out into the regions where the shadow should be, and it's not uniform. There are bright and dark areas. It's fuzzy, not sharp. This is diffraction. So you feel now that light doesn't travel in straight lines because you've seen it. But it all depends on what you mean. If you're looking for very small effects, hunting for minutiae, then it's true. Light doesn't travel in straight lines, and we've proved it. But as a first approximation, we can say that it does. The other effects are very, very small. We depend upon our belief that light travels in straight lines for all of the measurements that we make where we use light. I sight down a gun barrel to see if it's straight. We measure our fields and our forests by surveying, depending upon this same principle. We navigate our ships under the belief that light travels in straight lines. And yet you have seen that under the right conditions, light can bend a little bit. So let's look at some other experiments and see if we can find other ways in which it bends. Here's a beam of light going down this smoke box, traveling in straight lines. And I want to try to influence its path, change its path in three different ways. With this beam of light, or with a beam from this light source, with this charged rod, and with this magnet. This is a real strong magnet, and if anything should influence that beam of light, the magnet should. Of course, you probably don't believe these experiments will have any effect any more than I do. But let's try them anyway. If I take this card out of the beam here, then I get a push, or do I? I don't see any effect. This second beam, almost at right angles to the first, has no effect. The charge on this rod, as far as I can see, doesn't change the direction there, or there, or there. And this magnet, set on top, no effect. This way, no effect. No effect at all. So, none of these three outside agents had any effect on the direction of that beam of light. But if the light is going in that direction, in straight lines, then how do I see it up here? Obviously, the light must have been bent. The only thing that can do this is the smoke particles in the box. If you don't believe it, let's get rid of them. I can't see any beam from this angle, and I don't think you can either. So let's put in some more smoke. There's the beam again. It must be the smoke particles in the box that have bent the light. Actually, they send it out in all directions so that you can see this beam from almost any angle. This, then, is the second way in which light can be bent. We call it scattering. The first way, you remember, was by diffraction, when light goes through a narrow slit or bends around the edges of obstacles. Now, a third way is by reflection. You're already familiar with that. You know what a mirror is. But here's a piece of material that you wouldn't ordinarily associate with a mirror, a piece of slate. It doesn't act like a mirror at all until I begin to hold it up toward a bright source of light, and then the surface gets bright. And when I get it up near grazing incidence, I can actually see the light source as though it were being reflected in a mirror. It's quite bright and clear and sharp. And when I come back down again, it disappears. Now, an ordinary mirror and this piece of slate are both opaque materials. Is this why they reflect? We can test that by using a piece of glass. You know glass already reflects because you've seen yourself in a window at nighttime. But if I hold this piece of glass up about in this angle here, I can see that light reflected in the surface. When I bring it up toward the light at grazing incidence, the reflection is quite bright again. And when I take it down, it's still acting quite a bit like a mirror. Now, of course, this is a pretty thick piece of glass that I've used here. I can test a thin piece by using a piece of sheet plastic mounted on this frame. It's the kind you use to wrap foods. The same sort of thing happens. I can reflect it into the camera. I can look at the source over there. I can see the reflection down here. It gets brighter again and somewhat clearer as I get up toward grazing incidence. So this thin film acts like a mirror, too. But this film is thin only in comparison with the glass. We can do much better. Let's go to a really thin film and see what happens. This apparatus consists of a broad-beamed light source shining into a box over here that has a soap solution in a dish in the bottom. If I put this brass ring down slowly into that soap solution, then pull it up carefully, a soap film forms on that ring. The inside of the box is black so that you can't see light by transmission. Instead, you're seeing the light by reflection from that soap film. Watch it again closely. Those colors you see are made by the light reflected at both the front and back surfaces of the soap film. They twist and turn as the material of the soap bubble flows along the surface. Actually, the soap bubble forms a wedge thicker at the bottom than at the top, and the thickness of the wedge determines what colors you see. Why this happens, you'll study later in the course. Notice the dark area at the top of the ring as the material flows down the bubble. If you think there isn't any soap film there, watch what happens when I stick it with a pin. There's a fourth way in which we can change the direction of a beam of light. This is by refraction. Here's an ordinary fish tank, about half full of water. I put in a little fluorescein dye to help us later in our experiment. A beam of light coming down along this top board goes in a straight line, but when it hits the water surface, it changes direction. It bends down into the water. Below the water surface, it goes in a straight line again. But this change in direction is what we mean by refraction. It's a very common occurrence, but it poses some interesting problems. For instance, suppose you were a fish diver, skin diver, down underwater. How would things look to you as you looked up through the water surface? Or even, how would they look to you down below the water? Let me show you. We've taken our cameras to the MIT swimming pool. Our cameraman has special breathing apparatus that allows him to stay underwater without releasing air bubbles that would disturb the surface. This is very important, because if we ripple the surface, we can't see what we're looking for. Let's start first by looking at the bottom of the pool. It's quite clear. We can even see the lines between the tiles. As we look toward the side and up, it's still clear. And here are the feet of our swimmer dangling in the water. But look, as we move away, funny things happen. The body separates from the feet and gradually floats up and out of our field of view. In its place, we see a pair of reflected feet that we were not able to see before. All right, let's put her back together again and find out what's happened. You saw several complicated things happening all at once over there in the pool, and I can explain it to you with this card. This card shows a girl sitting on the edge of the pool, dangling her feet in the water. Originally, the camera was in this position, looking up toward the swimmer so that you saw her feet and her body above the water in about the normal position. But then the camera was pulled back toward here and tilted down a little bit to shoot over toward the swimmer in this direction. Now, some of the light coming from the top of her head came over toward the water surface this way and bent down toward the camera so that it seemed to be coming from up in the air. And some of the light from her legs came over almost parallel to the water surface until it hit and was refracted down into the camera so that her knees seemed to be up here. Her whole body seemed to float up in the air above the water. Let's try it again. This time we'll tilt the camera up in the air, and there she is. It's a lot of fun to see what happens with a bunch of swimmers. Strange looking sight, isn't it? Remember, if the diver is to see this, the water must be perfectly still. To show you some of the things that went on at the swimming pool under more carefully controlled conditions, let's go back to our fish tank. This time I have a mirror underwater so that the incident beam can be reflected from that mirror back up toward the surface. If I turn the mirror a little bit, then it reflects the beam up toward the water surface, and I see an emergent beam leaving the water, bending away from the perpendicular in the same way that the incident beam bends toward the perpendicular upon entering the water. By turning the mirror a little bit more, the emergent beam comes right straight up through the surface, showing no refraction at all. And turning the mirror a little bit more, I can put the emergent beam right on top of the incident beam so that they seem to be traveling along the same paths. Turning the mirror just a little more, and I begin to see a little reflection of light from the water surface down into the tank. A little bit more turn of the mirror, and the emergent beam completely disappears, and I see now a strong beam of light reflected at the water surface down into the tank. This we call total internal reflection. Now you can understand some of the things that happened down at the swimming pool. You remember those legs that stuck down through the water surface and the others that seemed to be up in the air above? We saw this pair of legs above by total internal reflection. Now, in the beginning of this film, when we started to study light, we thought that at first we would have to know what light is, but we very quickly decided that we needed to know instead how light behaves. So we did some experiments, and all of those were based upon the general principle that light travels in straight lines. But we also found that there are 4 ways in which light can bend. These were diffraction, scattering, reflection, and refraction. Now I want to show you one more experiment. This is a carbon filament lamp that can shine through holes that I will punch in this card over onto this ground glass. If I poke one hole in there, then I get one image over here. 2 holes give me 2 images, and 3 holes give me 3 images. And I'm sure that you believe firmly that these images, these pinhole images, were formed because light travels in straight lines. But if I add just a single lens in the path of these rays of light, then I find out here on the ground glass only a single image. This is your clue to begin the study of ray optics.